In this video, I'm going to talk about the fundamental theorem of line integrals. Now, we really want to think about the fundamental theorem of line integrals as the version of the fundamental theorem calculus just for line integrals. So let's start there. So we start with the fundamental theorem of calculus, a to b, f prime of x dx, and that's going to be equal to f of b minus f of a. So here is your fundamental theorem of calculus, learned in Calc 1, Calc 2, you worked in, where f prime is continuous on AB, but we also call this the net change theorem. So this integral depends on the net change from A to B. So we're evaluating, right? We're evaluating the antiderivative of f prime at B, at an endpoint B, minus the endpoint A. That's going to be very, very similar to what we got here with the fundamental theorem of line integrals. So we're going to take the line integral, and you've seen the line integral, now we're talking about line integral of a vector field. All right, so the line integral of a vector field, and I'm going to just put a vector over f to designate that, along C. All right, so this is the line integral of vector field f along C. We want to think of f being equal to this gradient vector. All right, so what we're just going to do is replace, I'm just going to put a little arrow. And we're going to replace the vector field in the line integral with this gradient vector. All right, so what this really is, right? What this really is the line integral of conservative. So this has to be a conservative vector field. The fundamental theorem of line integrals does not work if you do not have a conservative vector field. Well, why is that? Well, I didn't display it yet, but here it is. So you're talking about this vector field, which we're just designating as a gradient vector. Okay, you can imagine this being any vector field, right? Any vector field, except for the fact that this vector field has to be conservative. So we think of this as the derivative. So we think of the antiderivative as that potential vector, right? So we think of it as a potential vector f. And we're going to evaluate that at the point RB, and we're going to subtract it from the point f evaluated at the point RA. Right? So let's graph this. So we just think of a curve, some sort of curve here, right? And this curve goes from, we'll just say x1, y1, z1, right, to x2, y2, z2. All right, so from A to B. And there's some sort of vector field being applied on here. some sort of vector field. All right, we've got a vector field being applied on here. So we want to find the line integral of that vector field along C. This is C. Right. We're going to do that if the vector field that's being applied here is a conservative vector field, right? If it's a conservative vector field, then we can apply our fundamental theorem of line integrals. And we can say that that vector field, you could write F here, but I'm trying to designate that this is intended to be the idea of being a gradient vector. On this, so this vector field, this gradient vector, is going to be equal to the potential vector at B, x2, y2, z2, R, minus F at R, y1, or x1, y1, z1. So it's as simple as that in calculating, just like the fundamental theorem of calculus. So this is an analogous fundamental theorem of calculus. This is a fundamental theorem for line integrals. So in the three-dimensional space. Now, what I think we're going to do is, let's go to an example. So I'm going to go to the next, go to an example. All right. So this example is example 1 on that page 1088. So we have a vector field. So we're saying the vector field negative m, mg. All right, these are all constants, right? And then x is our variable. This vector x and vector x. All right. So this vector field really is this is the gravitational field, right? This is the field applied by gravity with mass and mass of the bodies and so forth. So here's our vector. We want to find the work done, right? So one of the main things for vector fields is the work done. The work done from applied to some sort of particle that's moving from. So this field provides some work done from the particle that starts at 3, 4, 12, 2.220. And yes, so C has to be, it's a smooth curve. So in this case, piecewise smooth curve. And the book had said, look at 16.1.4, and that describes that. So we already know that F is a conservative vector field, right? If F was not a conservative vector field, we wouldn't be able to apply this fundamental theorem for line integrals. But we can, right? So that means that there is a potential vector, and that potential vector, again, we're skipping kind of all the steps to get here, but this is your potential vector. Sorry, potential function. This is the potential function for the vector field F. So we're going to just find the work done moving from one point to another point. We don't really care. It's going to be independent of path, so we don't really care about the path here, right? We just care about the start point, end point. And again, that's the line integral of f, your integral f dot dr. And we can think of, which we did, we can think of f as that gradient vector. Think of f as that gradient vector. But we know by the fundamental theorem for line integrals that this is going to be just equal to f, right? Our potential vector f 2, 2, 0, minus 3, 4, 2, at those 2 points. And the book gives you the answer, and we get mg, whatever that big mg is in the problem, those constants, and your answer ends up being this. All right, so this is one example. This is a prime example of vector fields applied to smooth curves. We're talking about work being done. And this was easy to compute because we're just computing the endpoints.